Hello and good morning. Today we have a presentation for your training. Thank you for attending the presentation on atoms, bonds and structure. The purpose of the presentation is to explain how atoms bond together to form compounds and how different types of bonding influence the physical properties of substances. I will discuss metallic, ionic and covalent bonding, the role of electronegativity, how bonding affects physical properties, how electron pair repulsion theory can be used to predict molecular shape, and finally how intermolecular forces influence whether substances exist as solids, liquids or gases at room temperature. Our learning objectives are: by the end of this presentation you should be able to describe the three main types of chemical bonding, explain the importance of electronegativity, understand how structure affects physical properties, predict molecular shapes using electron pair repulsion theory, and describe the role of intermolecular forces such as hydrogen bonding and van der Waals forces. Firstly, we're going to look at the importance of understanding atomic structure. Atoms consist of protons, neutrons and electrons. Protons are positively charged, neutrons are neutral, and both are found in the nucleus. The electrons in the outer shell, known as valence electrons, determine how atoms bond. Most atoms are not naturally stable and will gain, lose or share electrons in order to achieve a full outer shell, similar to the noble gases. Now we'll look at metallic bonding. Metallic bonding occurs between metal atoms. Metals lose control of their outer shell electrons, creating a lattice of positive metal ions surrounded by a sea of delocalized electrons. These electrons are free to move throughout the structure. Strong electrostatic attraction between the positive ions and delocalized electrons creates the metallic bond. This explains why metals are strong, conduct electricity, and conduct heat efficiently. Examples are copper, aluminium, and iron. On to the next slide, which is ionic bonding, which we can see here. Ionic bonding occurs between metals and non-metals. Electrons are transferred from the metal atom to the non-metal atom. The metal becomes a positive ion and the non-metal becomes a negative ion. Strong electrostatic attraction between these oppositely charged ions creates an ionic bond. Sodium chloride is a common example. Sodium loses one electron while chlorine gains one electron. The resulting ionic lattice forms a strong and stable structure. We now move on to covalent bonding. Covalent bonding occurs between non-metal atoms. Instead of transferring electrons, atoms share electrons. This sharing allows both atoms to achieve stable outer electron shells. Water, methane, and carbon dioxide are examples of covalent compounds. Covalent bonding can produce similar molecular substances or giant covalent structures depending on how the atoms are arranged. We now move on to electronegativity. Electronegativity describes the ability of an atom to attract electrons towards itself in a chemical bond. Elements such as fluorine have very high electronegativity, while metals generally have lower electronegativity. A large difference in electronegativity usually results in ionic bonding because electrons are transferred. Smaller differences produce covalent bonding because electrons are shared. Understanding electronegativity helps explain why different bond types form. The properties of ionic compounds are that they have high melting and boiling points because large amounts of energy are required to overcome the strong electrostatic attractions between ions. They are usually hard, brittle, crystalline solids. When solid, ions cannot move and therefore cannot conduct electricity. However, when molten or dissolved in water, ions become mobile and can carry electrical charge. The properties of metallic structures are that metals conduct electricity because their delocalized electrons are free to move throughout the structure. They are also malleable and ductile because layers of metal ions can slide over one another without breaking the metallic bond. These properties make metals useful for electrical wiring, construction and manufacturing. We now move on to simple covalent structures. Simple covalent molecules contain strong covalent bonds within molecules but have weak intermolecular forces between the molecules because relatively little energy is required to overcome these intermolecular forces. Simple covalent substances generally have low melting and boiling points. Many exist as gases or liquids at room temperature. Examples include methane, oxygen, and carbon dioxide. We now move on to giant covalent structures, which consist of a vast network of covalent bonds extending throughout the material. Diamond and graphite are common examples because many strong covalent bonds must be broken before melting can occur. These substances have very high melting points. Diamond, as we all know, is extremely hard because each carbon atom is bonded to 4 others. Graphite, as we know, is softer because it contains layers that can slide over one another and it can conduct electricity due to the delocalized electrons. So now we move on to electron pair repulsion theory. Electron pair repulsion theory states that electron pairs surrounding a central atom repel one another. To minimize repulsion, they arrange themselves as far apart as possible. This theory allows chemists to predict the 3-dimensional shapes of molecules and ions, which can influence their physical and chemical properties. Methane, as we see a diagram of methane here, contains 4 bonding pairs surrounding a central carbon atom. Because all 4 electron pairs repel equally, they arrange themselves tetrahedrally. This results in bond angles of approximately 109.5 degrees. Methane is therefore described as having a tetrahedral shape. I'll move on to the ammonium ion, which contains 4 bonding pairs of a central nitrogen atom. These electron pairs arrange themselves tetrahedrally to minimize repulsion. Ammonium is an example of a dative covalent bonding, or can also be called coordinate covalent bonding, which is a type of covalent bonding, which we see in the explanation here, where the atom supplies 1 electron pair. Here, 1 atom provides an unshared lone pair to an empty orbital on another atom, as you can see in the diagram here. Intermolecular forces are attractions between molecules. Although weaker than chemical bonds, they have significant effects on melting points, boiling points, and physical state. The main types are van der Waals forces, permanent dipole-dipole attractions, and hydrogen bonding. The stronger the intermolecular force, the more energy is required to separate the molecules. Now, our final bit is hydrogen bonding. Hydrogen bonding is the strongest common intermolecular force. It occurs when hydrogen is bonded to highly electronegative atoms such as oxygen, nitrogen, or fluorine. Water molecules form hydrogen bonds with one another, which explains why water has a much higher boiling point than expected for a molecule of its size. Hydrogen bonding is also extremely important in biology because it helps maintain the structure in proteins and the double helix of the DNA structure. Conclusion. In conclusion, chemical bonding plays a fundamental role in determining the physical chemical properties of substances. Metallic, ionic, and covalent bonding arise from different electron attractions and electronegativity differences. Structures influence conductivity, hardness, melting point, and physical state. Thank you for listening.